So let's talk about the third way you can program parallel systems in Java. And this is by using the so-called Reactive Streams paradigm, Reactive Streams model. And it's essentially an asynchronous programming paradigm that focuses on processing streams of data and propagating changes between publishers and subscribers and doing the whole thing asynchronously, if you so choose. And we'll see that there's different variants of this, but commonly you want to do it asynchronously if you can. So there are four key principles in the reactive programming paradigm. And if you want to read more about this, go take a look at reactivemanifesto.org. You can't have a new paradigm without a manifesto. So we have the Agile Manifesto. We have the Reactive Manifesto. We have the Communist Manifesto. There's lots of manifestos. These are not all equally at the same level of abstraction. But you can see here that the four key principles in the reactive programming paradigm or the manifesto are these four things. So let's talk about them. Responsive means the ability to provide rapid and consistent response times. That really comes back to this issue of latency. We want to be able to make the response be as low latency or as quick as possible, and we'd like it to be fairly consistent so you don't have large gaps or delays where sometimes it's responsive, sometimes it's not. Another principle is resilient, and the idea here is the system should remain responsive even when things go wrong. And inevitably, even if you do the best you can in large-scale systems, especially when you work with teams of people, not all of whom are equally well-versed in the art of parallel programming, sometimes you have problems with the infrastructure not always working, sometimes you have problems with the requirements not being fully fleshed out, or the design, and so on and so forth. Things will fail. And what you'd like to be able to do is make sure that if something fails, you don't end up with the whole system coming tumbling down. So you want to be able to survive partial failure. That's a really key theme. And reactive programming supports that in various ways that we'll talk about. Another goal is to make the system be elastic. And what that means is as the workload grows to some point, you want the system to be able to continue to be responsive even though there's more work to do. And we talked a little bit about that before. And then finally, and this is a little different from the other principles, you would like the design of the system to be done in a so-called message passing or message driven way. And the idea of doing this is to enable asynchronous message passing that ensures loose coupling between components, thereby making them more plug and play. You can replace one without breaking other things. More scalable because you can add more threads to be able to do things. You can add more subscribers with more threads to be able to handle the workloads of more publishers. You want to isolate stuff so you can make it more resilient because a failure in one part won't necessarily propagate everywhere else. And you also would like to be able to make things location transparent, which means that you can take some of the work and move it to other parts of your system. In particular, with modern microservice-based architectures, you want to be able to have your clients that are making calls and your servers that are implementing calls stretch out so they don't all have to run on the same computer. You can run some parts of the services or microservices in other computers within a distributed or networked computing environment. So those are the four main principles of reactive programming. Java provided support for reactive programming in Java 9, although it was fairly limited. And it was done through something called the Flow API. And here's what the Flow API looks like. You've got four interfaces that are part of the Flow interface. One is a publisher, which can send data, and it sends data to a subscriber, and the subscriber has ways of being able to handle that data. And then you can also have these things called processors, which are both publishers and subscribers, so they can generate events, and they can also consume events or subscribe to events. And then there's also this thing called a subscription, and the subscription is something that you can use to indicate to a publisher how many events it should send until the subscriber says, okay, fine, I'm done processing those events, send me the next chunk. And this is to handle essentially flow control, where you don't want fast publishers overwhelming the resources of slower consumers. As you'll see, the main approach here is based on something called the publisher-subscriber pattern, and that in turn is based on two other patterns. These patterns come from the Gang of Four book, the good old Elements of Reusable Object-Oriented Software book, the Design Patterns book. And the two patterns are iterator, which is a pull model where the subscriber or subscribers pull a certain number of items from the publisher, which is the source. So the subscribers are the sinks, the publisher is the source. And then we also have the observer pattern where you can have multiple subscribers receive data that's pushed by a publisher. So in this case, the publisher is the source, and it pushes data to 0 or more subscribers, and that's the observer pattern. So iterator pattern, observer pattern. Hopefully you've encountered some of those patterns in other classes as well. We are going to see 2 popular implementations of reactive streams, one of which we'll focus on this course, one of which we'll focus on in my sibling course that I teach in the spring, which is RxJava, which is one very popular implementation of reactive streams, and the other is Project Reactor. RxJava is a little older. Our Project Reactor is a little newer. They both do more or less the same thing. We're going to focus on RxJava in this course. These frameworks, these implementations of reactive streams provide a bunch of methods like subscribe on, publish on, observe on, and so on, which are called operators. And these are used to map events that are sent by publishers to threads and or thread pools. And that's the way we're going to get parallel computing out of this particular approach. There's also a whole slew of schedulers that are provided by both frameworks that can dictate the way in which incoming events are processed by one or more threads. And there's a whole slew of these things. We won't talk about them right now in detail. We'll talk about that later. But in a nutshell, some of the pools handle I/O-bound tasks. Some of the pools handle compute-bound tasks. And your job is to know which one to use under the right circumstances. There's also some very cool parallel programming classes that are provided, such as parallel flowables and other mechanisms for parallel computing. And this makes it possible to be able to map the requests to underlying cores in a nice reactive way. So there's pros and cons with this, of course, too. The pros are that you can have a nice parallel computing model with a very small number of threads using these thread pool mechanisms that are supported by schedulers. That's one thing that you can do. This will allow you to scale up performance with relatively few resources. There's a link here that shows how you can get much better scalability by using reactive techniques versus the classic synchronous approaches to doing things like building web servers or web-based applications using web servers and web services. Another nice thing which kind of carries over from the parallel functional programming techniques we talked about before, you don't typically need threading or synchronization explicitly. These frameworks handle that stuff. That, again, reduces inherent and accidental complexity. And a nice thing is that this pattern, this paradigm, integrates streams, asynchrony, and publisher-subscriber models cleanly. Parallel streams and completable futures handle streams and asynchrony, but not really pub-sub, whereas reactive programming adds pub-sub to the mix and integrates streams and asynchronously more effectively. Once again, there are some downsides. One of the most challenging is that it takes a while to get your head around this model, and so it's not appropriate in all situations. Once you take this class, of course, you'll be well-versed to use it effectively, but a lot of people struggle because it's not the most intuitive way of programming at first relative to traditional synchronous programming. So there can be a steep learning curve, but we will overcome that together. And we're going to be talking about reactive streams later in the course, and I'll show you where and when to apply it. And this will focus on reactive streams, which will be RxJava. We're going to focus on RxJava as the framework, the implementation of the reactive streams paradigm. So that is the end of the third part of this discussion about how parallel programs are developed in Java. You will get experience with all 3 of those approaches here throughout the semester.